When we look up at the night sky, it's tempting to picture the universe as a vast stage where stars float in a static void. Albert Einstein proved that wasn't the case. His equations revealed that space and time are actually woven together into a continuous, flexible fabric. Look at this grid representing space-time. When you place an incredibly massive object onto it, the fabric physically dips and bends under the weight. This flexibility creates two distinct cosmic extremes. We have observed one of them actively tearing through galaxies, while the other exists entirely on paper as a mathematical dream. To understand how the universe actually operates, we have to look at what happens when this cosmic fabric is pushed to its absolute breaking point. When a massive star burns through the last of its nuclear fuel, it can no longer support its own immense weight. The core rapidly implodes, crushing an entire star's worth of matter down into a single, infinitely dense point. We call this point a singularity. It possesses infinite density, and at its exact center, the standard laws of physics simply stop working. Surrounding the singularity is the event horizon. This distinct boundary separates the collapsed star from normal space. The gravitational pull here is so intense that nothing can break free. Even light cannot achieve the escape velocity required to leave. Anything that crosses the event horizon is claimed permanently, making a black hole the ultimate inescapable trap in the cosmos. For decades, black holes were treated as mathematical ghosts. They were quirks hiding in relativity equations that physicists assumed could never exist in nature. Then, modern astronomy caught up. We watched stars wildly orbiting invisible heavyweights at the center of our own galaxy, and we detected the physical ripples in spacetime from massive objects colliding in the dark. This image provides our first direct visual proof. It shows a blurry ring of glowing light circling a deep central void, a real event horizon, finally caught on camera. This subsequent image gives us an even clearer look at the structure. We can observe an accretion disk of superheated matter actively swirling around the invisible center. Black holes have left the chalkboard entirely. They are real, terrifyingly heavy objects anchoring entire galaxies in place. If extreme gravity can warp space into a dead end, we have to ask whether that same math allows the fabric to bend in a way that creates a shortcut. This brings us to the theoretical opposite of a black hole, the Einstein-Rosen bridge, commonly known as a wormhole. Imagine space as a flat sheet. Traveling from point A to B requires tracing a slow line. A wormhole bypasses this entirely. By folding the paper in half, we bring the distant points together and punch a tunnel directly through the overlap. In theory, this tunnel could connect two completely different regions, allowing us to instantly cross millions of light years without ever breaking the universal speed limit. The math perfectly outlines how this folding could occur, but physical reality immediately throws up a massive roadblock: structural stability. The equations indicate that the moment a standard wormhole forms, its own extreme gravity would cause it to crush itself. It would snap closed faster than a single photon could make the trip. To prevent a collapse, we would need a hypothetical substance called exotic matter. Possessing negative mass and gravity, instead of pulling objects in, it pushes space outward. This acts as a structural brace, holding the throat permanently open. We have never discovered exotic matter, nor any evidence that it exists naturally in our universe. Without it, wormholes remain firmly locked out of reality. These two concepts represent the absolute edges of human understanding. One maps the physical limits of crushing matter, while the other tests the limits of our reach across the cosmos. Black holes force us to accept that the universe contains forces so violent and extreme that they casually erase the laws of physics we rely on every day. Wormholes challenge us to look past those terrifying extremes. They encourage us to do the math and dream of a time when the vast, isolating distances of space might finally be conquered. Whether we are looking at the inescapable darkness of a dead end or imagining a bridge to the stars, we are observing a cosmic architecture that is endlessly strange and wonderfully complex.